thanks to the organizers, and I think I should say surprise. So this is joint work with Neeraj Kayal, Sebastian Tavenas, and Chandan Shah. And yeah, as Marcus said, it's reconstruction of full-rank algebraic branching programs, and we'll get on with it. So I'll firstly define what is reconstruction. You have oracle access to an m-variate degree D polynomial F, and you're also given that it's computable by a size S arithmetic circuit, and it's coming from the circuit class C. And what we expect as an output is a small circuit, preferably from the same circuit class, and it's computing F. And the wishful time complexity is it should run in polynomial in the number of variables and the S that you have been given, and beta, where beta is the bit length of the coefficients of F. So just to be pedantic, since you're using beta, we keep the field is Q, and the result also holds for large characteristic fields. So reconstruction is seemingly tougher than PIT and lower bounds, but it's also observed that techniques for PIT and sort of lower bounds can be used to give reconstruction for specific circuit classes. Like the techniques that have been used to, the measures, for example, that have been used to show lower bounds for a specific circuit class, that have been used to give reconstruction algorithms for some reduced version of the circuit class. And what's important to note is that even though polynomial identity testing has an efficient randomized algorithm, reconstruction in general doesn't have. At least we don't know till now. And so I've just pointed, so even efficient randomized algorithms for reconstruction are sort of wishful. And these are two randomized algorithms that I've just listed down. So Gupta, Kayal, and Locum, they gave an efficient randomized algorithm for multilinear depth 4 circuits with 2 product gates at level 2. So I guess depth 3 circuit was introduced. It's in the same spirit. It's sigma product, and the top fan-in is just 2. That's what I mean by 2 product gates. And recently, Gaurav Sinha also gave depth 3 circuit with top fan-in just 2 for characteristic 0 fields. And these are efficient randomized algorithms. And as you can see that even giving randomized algorithms is quite non-trivial. Like the models are quite restricted. So this sort of drives the question that can you forget about worst case scenarios? Like you forget about some set of circuits, but can you reconstruct on an average for most circuits in the circuit class? And this puts forward the following question. Like you ask whether if the input polynomial is coming from a distribution from the underlying circuit class, and can you now reconstruct with high probability? And this question sort of initiated this work, and already this was looked at for some important models like random multilinear formulas. Gupta, Kayal, and Locum, they gave efficient randomized reconstruction algorithm, and even for arithmetic formulas, that's quite a strong model, and they gave again a randomized algorithm. So this sort of motivates the model and the question here. So the model that we are looking at is algebraic branching programs, and it's slightly stronger than arithmetic formulas. At least the equivalence is not known. So an algebraic branching program is defined as follows. It's a product of D matrices. It was defined by Guillaume, I guess, in product of D matrices. X1, XT, where X1 and XT are and xi is a wi cross wi matrix. The entries in these matrices are just linear forms. So you could also have affine forms, but without loss of generality in this work, you can assume they're linear forms. You can reduce it to the following case. And we say that the ABP as, we say that f is the polynomial f computed by the ABP is just the entry in the 1 cross 1 matrix. So this is a 1 cross 1 matrix, and the polynomial computed by this ABP is just the polynomial entry in it. And we also say that the ABP has width W. So this is just a notation. So it's computed by a with W ABP, it's a vector, and so on. So as I said, we are looking at average case reconstruction. So I need to define a distribution on this ABPs, and the distribution is quite natural. It's just you pick the linear forms random, the coefficients of the linear forms randomly, independently and uniformly at random. Yeah, just to be precise, you can fix a subset of the field S gamma where you have gamma bits on the left and right of the decimal. Your field is Q, and you pick independently and uniformly at random the coefficients from S gamma. So just to be sort of precise, what is picking randomly?
So all the entries and the matrix are homogeneous?
Yes, homogeneously. Linear forms meaning, so there are no affine constants, yes. I'll specify it. You first fix, I'll write it. You first fix the width and the number of variables, and then you sort of, yeah, good question. So fixing W means fixing the structure of the ABP. You sort of fix the structure, and then you pick the coefficients of the linear function. Fine. So, some notation. I should have used. Okay. Suppose x1, x2, xd is WABP. So x1, x2, xd is a width WABP, and so I would use n to denote the total number of linear forms in the matrices combined. like the number of linear forms in x1 plus the number of linear forms in x2, and so on. So what our main result states is we give an efficient randomized algorithm for average space reconstruction when m is greater than or equal to n. So m is the number of variables in your input polynomial, and n is the number of linear forms that is it's being computed by the full rank ABP. Yeah, I think. Yes. Okay. Yeah. It's just the total number of linear forms. Yeah. Yeah, so a crucial point to observe here is that if m is greater than or equal to n, then with high probability, the linear forms that you're choosing would be f-linearly independent. It's a very easy argument. You can, so the linear forms in x1 to xd Yes, 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 yes. That's what I initially said, just to be. Yes, so the time complexity is poly in m comma beta. Beta is the bit length of the coefficients of f. So it yeah, not of the linear forms. This is like. But it would be sort of depending also on the coefficients of the linear forms that you are choosing. But yeah, it's just because you have black box access to f, and whatever you're doing only depends on the coefficients of f. It's just depending on the coefficient length of f. The linear forms in x1 to xd are f linearly independent. With high probability. And this sort of motivates the model full rank ABPs. So full rank ABPs are simply where
also because the linear forms could be coming from an infinite the sample space is infinite.
yes. So that's why I fixed the bit length. Like we fix the bit length so that you can be
Even when it's rational numbers.
yes, yes.
It could still be each linear form comes from an infinite sample.
No, you are sampling linear forms only from this bounded coefficient.
Bounded coefficient. As so your coefficients are bounded by 2 raised to gamma, right?
No, but which are the linear forms which are independent? The ones which you have randomly.
Yes, which you have randomly picked. So I think there is some confusion. Yeah. So the linear forms are summation ai xi, and you sort of pick them, the ai's independently and
But AI is a bounded bit length.
yes, ai's are of bounded bit length.
Beta.
Yes, beta. not beat up gamma, but yeah, it's still it.
Beta is
Yeah, but you can.
known, right, up there.
Yeah, it's not. It's just no. It's the in.
No, all I meant was that if you fix beta alone,
Yes.
then AIs could still potentially come from.
Yes. Yes. But you don't fix betas. You fix AI, the bit length of the AI. Yeah, that is what I was actually trying to say. That it, even though you fix that, the coefficients only, since you're doing black box algorithm. Yeah. Yes, it's possible. Or at least I don't know. Like, yeah, like I don't know examples where it's possible, but I believe it's possible. Like, so that is why I was specifying on beta. Yeah, that's the reason that I said it's on beta. The linear forms in x1 to xn with high probability. Yeah. Yeah, it's just this definition. The linear forms, all the linear forms are F-linearly independent. And the algorithm basically does this. You're given an input m-variate polynomial, and it begins by assuming that it's computable by a full rank ABP, and it sort of goes through the algorithm, and it outputs a full rank ABP, and eventually it does a PIT test to check whether F is equivalent to the, whether F is equal to the polynomial computed by this full rank ABP. And if initially your premise or your assumption was wrong, then this PIT test should catch it with high probability. So I hope that's clear. So for the rest of the talk, we'll assume that the input polynomial F is computable by a full rank ABP. No, it's not unique. I'll come to it. That's precisely that I want to say now. But there is some uniqueness that goes into reconstructing it, and I'll specify it.
This algorithm you fix an n less than n, and then you run this.
So you have W, right? You have W. Yes, W is given to you. M and W is given to you. That's the distribution that. So you fix M, and you fix W. Then you pick your random ABP, and then that gives you the N as well. And the problem, that the theorem is saying that if M is greater than or equal to N, then you are able to reconstruct with high probability. Is it okay? Yes. Huh? Yeah, so this is can you repeat your question? Yeah.
I mean, you don't pick the polynomial.
Yes.
He is picking it inside the
Yes,
black
yes.
box.
So the algorithm actually doesn't need to know the W. We can actually construct the W.
Okay.
Yes. So it fits into the paradigm. You actually don't. So yeah, I made a slight mistake. You don't need to know. You don't need to know the W. You can actually give back the W. The algorithm just gets black box access to an m-variate polynomial f, and it starts by assuming that it's computable by a full rank APP. And then, if it is, then it will actually output the W as well. Yeah, the upper bound on W is the number of variables.
Yeah.
Full rank APPs. Okay. Yeah, so there is a follow-up work that by the other three authors of this work that actually solves this problem with where you have access to a product, matrix product, you have access to a matrix. Now this is not a 1 cross 1 matrix. It's a W cross W matrix, and all are uniform, like they're square matrices, W cross W matrices, and you have the entries are again linear forms. But the restriction now is just that the number of variables M needs to be greater than W square. So it's not, the restriction is not that the number of variables needs to be greater than the total number of linear forms, but just the number of linear forms in one specific matrix. And they are able to reconstruct even in this case. And this has consequences for matrix factorization and so on. So, yeah. Just wanted to mention it. Okay, so let's get back. Wonderful. Yeah. Yeah, coming to Ramprasad's point, that suppose your input polynomial f is, yeah, before I begin with the argument, I just want to state one more thing. So that you can actually reduce the number of variables from m to n. There is a variable reduction step, some pre-processing. If f is, so the algorithm begins by assuming f is computable by a full rank ABP. And it can do this pre-processing step where it actually reduces so it's called the redundant variables. It removes the redundant variables, and now you can assume that the number of variables, effective number of variables in f is actually n. So now we will assume that the number of variables in f is n. And this can also be done in black box. Computable via full rank ABP. So from this full rank ABP, I want to sort of construct new full rank ABPs and see how they can be constructed. This is exactly what you were asking, right? So there are primarily you can see there are three kinds of transformations that you can do and sort of construct new full rank ABPs. So the first is that transpose. This again computes the same polynomial. The second is the left-right multiplication. Your x1 is where AIs are in GLW. AIs are invertible matrices, and you just do left-right multiplications. And so this one is slightly non-trivial. We call it the corner translations. Yeah, so your x1. Yes.
When you do this left-right multiplication, you insert these AIs to get this student, they are over the field.
Yeah, they are on the field, but it's okay, right? So you sort of, now you consider the product x1 prime.
No, the product is the same. That
Yes,
clear,
but this is not algorithmic. There is nothing going on with it.
No, no, no. What I meant was that, so the entries are now, you were saying that the entries are linear forms, but now you have
Yes,
entire matrices, so the entries are just field constant.
yes, field constant. But this is there's nothing algorithmic going on here. I'm just trying to say that these are sort of the kinds of full rank ABPs that you can generate. So that question that you're asking, that would come into the picture of you're asking the bit length of the coefficients.
No,
Oh,
I'm saying
sorry.
that this full rank ABP that you have produced is of a different type.
Yes, it's
also allowing.
Yes, yes.
What I understood earlier is that you're not been considering those kind of.
No, I guess you're observing the AI into one of the layers.
Yeah. Yes.
When you multiply these three things together, you get this new
So you actually do the multiplication.
Yes, yes. So you're considering this product x1 prime. X1 prime is
So these are still homogeneous linear.
yes, 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 yes. Okay. Sorry, there was some miscommunication.
Reconstruction is up to these transformations.
Yes, up to this transformation. These are exactly the symmetries. Yeah. So, yeah, so your x1 prime is x1 and, sorry, xi prime. So you remove x2 and xd minus 1. I'll state the transformation for x2 and xd minus 1. Is it okay? Yeah. The other matrices are same, and now you take So these are antisymmetric matrices. I'll tell you what the construction is. So you construct a matrix P or P2 where the ith column is the ith column of this matrix P2 is Bi yi transpose, and now it's yi xi transpose. There are only x's, yeah. Bi xi transpose, and it's easy to see that xi times Bi times xi transpose is 0 because Bi's are antisymmetric matrices. You look at the first matrix x1, and x1 Bi x1 transpose is 0 because Bi is an antisymmetric matrix, and so the construction is simply x2 is equal to your x prime to x2 plus P2. So your ith column of P2 is just Bi x1 transpose, and so now if you just look at x1 prime, x2 prime, it's just equal to x1, x2. It's because x1 prime, x2 prime would be equal to x1 into x2 plus P2, and x1 into x1 P2 would be 0. Is it fine? So the construction for the the other part, that is x prime d minus 1, would be similar. You look at these antisymmetric matrices, bd minus 1 to bd minus 1, wd minus 2, and you fix the rows of the matrix, like, I'll just write. The construction is similar, and it's easy to see now that x1 prime, x2 prime, huh?
X1 prime is X1.
Yeah, x1 prime is x1. So you take xi prime equal to xi for all d minus 1. And just the second matrices and the second matrix and the last but one matrix. You sort of do this translation. And this is because you have this, the first matrix and the last matrices are just row and column vectors. That is why you get this sort of action. Okay. So now what it turns out is that any full rank ABP that is computing F is sort of obtained by multiple such transformations. There is no, like any new full rank ABP that you want to sort of generate or compute, that computes F, it's sort of generated by this set of transformations, repeated actions of this transform.
Go from one to another by doing.
Yes, repeated. Yes, that's exactly what I mean. And so the way we come to this is, observe that in any of these transformations, the space of the linear forms, so I denote and x1, 2, and t minus 1 comma t. The linear forms in x1 and x2. So xi denotes the bracket xi, that denotes the space of the linear forms in xi, and x12 denotes the space of the linear forms in matrices combined x1 and x2, and so for xd minus 1 xd. And observe that in all these transformations, if you leave out the x2 and the xd minus 1 matrix, the space of the linear forms sort of remains same. The transformations are not changing the space of the linear forms. And this is exactly what we can prove for full rank ABPs. And this is the uniqueness property that allows us to reconstruct the full rank ABP. So this is a crucial lemma. If suppose f is computable by a full rank ABP, full rank ABP of x1, x2, xt of with w, then and if x1 prime, x2 prime, xd prime is a with w prime ABP computing f, then either x1 xi prime is equal to xi for I in D and x and so what we are able to show is that if f is computable by a full rank ABP x1, x2, xd of width w, and if x1 prime, x2 prime, xd prime is some other full rank ABP computing f of width w prime, then the layer spaces, so you take out the second and the last but one matrices. So the layer spaces of for these are equal. So this is the space of the linear forms. Denote xi as the space of the linear forms. Yeah. So this is an F linear space, right? You look at the linear space generated by the linear forms. No, no. Span of the entries of the. Yes, space of the linear forms. It's okay? Yeah, so xi prime is equal to xi. So the space of the linear forms is equal to the space of the linear forms of the original, or the inversion happens. That is because of the transpose operation. And so I'll not write it down. It just says that x prime d is equal to x1 and so on. And it's just the inversion. Okay, so unique. Yes, yes, exactly. That is why we are able to return the W as well. Yes. Yeah, so this W prime is equal to W is also crucial.
If you have an arbitrary homogeneous polynomial,
yes.
You cannot give a full rank ABP of where
no, no, but
is that true or not?
no, no. Full rank ABP models are incomplete. There are polynomials that cannot be computed by it. So this is also easy to show. It's by algebraic rank. So yeah, I can tell you later. Yeah, the model being incomplete also is some sign that you can reconstruct for it. No, so at least I don't know. I was trying to give a hitting set for this model for a full rank ABP. So this is non-zero, but hitting set I don't know. So, but this is like you have IMM, and then you are sort of doing IMM A times X, and now you are asking for a hitting set for this, where A is sort of full rank. At least I don't know. Yes, exactly. That's, yeah, exactly. Not, yeah. It's non-zero, but you don't know of a hitting set. At least I don't know.
When the linear forms are affine.
No. What?
If the linear forms are affine, not
Yeah.
homogeneous.
Yes.
In that case also you said it can be solved using this idea.
The PIT or this can be solved for affine forms. It's just that, so you just do this, you find out the homogeneous components, which can be done in black box. Or you can do a translation, and then you do a translation equivalence test. You find a translation point such that these are. Yeah. Yes, maybe. Yeah. Yeah, sure. Yes, that I am coming to. This actually characterizes the group of symmetries of IMM. I'll state it now. And this lemma actually helps you to characterize the group of symmetries of IMM, the way that I'm going to define IMM. Yes. So, okay, before this, I think I want to. So this is just a polynomial computed by product of matrices y1 to yd, where the width is again w vector, and the entries are formal variables. Each of them are entries are formal variables. So in literature, it's considered to be uniform width, but for our interest, we are considering variable width here. And so it's easy to observe that if f is computed by a full rank ABP, so I'm assuming that f has n variables. If f is computed by a full rank ABP, then there is an A in GLN. So you are replacing each variable just by a linear form. So it's A times X. And you can sort of associate these variables with the variables of F as well. That's crucial. Okay, so this lemma also helps us to characterize the group of symmetries of this polynomial, and that's another result that is, so, yes, sorry. Iterated matrix multiplication polynomial. Yes. No. So this, I explained this polynomial. Sorry, I didn't write it down. Sorry, my writing is bad. y1, y2, yd, the entries are formal variables in each of them. The linear forms are just, and so this is also a full rank ABP by trivial definition. And now it's just saying that you replace each variable by the linear form, a times x. So this is easy to see. This is so these are essentially the transformations that give you the group of symmetries. And so it's easy to see that this forms a group, left-right multiplication, the transpose, and the corner symmetric, anti-symmetric translations. So I probably write it down. So yeah, here if okay, I should probably state it more formally. Consider IMMW, which is equal to y1, y2, yd. So you have three transformations, exactly that the way I defined it there. The transposition, so the transposition works only if your wk is equal to wd minus k for all k in d minus 1. That's because of this. The width is unique. So it's either this way or it's either the reverse. So if the transposition is sort of wk equal to wd minus k, then you have two matrices. Otherwise, it's just a trivial matrix, the identity. And the left-right multiplication, and the corner antisymmetric translations. And what it says is that your GIMM is the semi-parallel. So this denotes the group of symmetries of this polynomial IMMW. This is equal to C semi-direct product H, where your H is also equal to M semi-parallel product. So it's generated by, the crucial part is it's generated by these three transformations. And that's essentially pinning down the full rank ABPs. That's the crux of the argument. How much time do I have? 10 minutes? Okay. So, yeah. So I'll just give some ideas as to how we go about the proof of this. And yes. I didn't understand. Set. Meaning? Oh, the bit length of the, of what? Of? Yes. So this is exactly what I was trying to state beginning also, that the theorem statement, it's poly m beta, where beta is the bit length of the coefficients of f, and the algorithm is black box. You are only allowed to evaluate the polynomial at points. So then everything is determined by the bit length of the coefficients of f. So does that answer your question? What do you?
But then, see, that may be represented by if you give the full freedom to choose whatever coefficients you want. But why would you know that it can sit in a particular box? That exercise can have bounded solutions with bounded forms.
Yes. Yes. Yes.
So the fact that the coefficients of my f are small,
Yes.
basically tells me that evaluating
Yes.
f at various points, I still get some.
Yes. Exactly. Yes. Yes. Yes.
And you're going to run
Yes.
the algorithm on top of it, and I guess learn the spaces.
So I don't care if some other representation has higher bits. The representation that I would be outputting would be poly beta. The representation that I am going to output,
That is what I'm interested in.
that is a consequence of the algorithm.
Oh,
That is a consequence of the algorithm. Yeah. Maybe I can tell you later. Yeah. Yeah, so there is a vector space that we look at associated with the polynomials to actually pin everything down. So I'll just state it. Yeah, it's called this fancy word, Lie algebra of the group of symmetries of a polynomial. So I don't understand much of this, but all you need is a vector space property of this. The algorithm only uses the vector space property. And so we denote it by GF. So A belongs to GF. A equal to G, yeah. Summation Aij, Xj, yeah, if it satisfies this equation. Aij xj derivative of f by derivative of xi. It's like the one order shifted partial. Yeah, it's okay. You just take the derivative with respect to variable and then you shift it.
G sub f is the Lie algebra.
Yeah, g of f is the Lie algebra. So A is in this Lie algebra if it satisfies this equation. Yeah, so what we do is we study the Lie algebra of IMM to begin with, and if f is sort of computable by a full rank ABP, it is, so I'll just define this equivalent polynomial. F is equivalent to n variate f is equivalent to n variate g if there exists A in GLN such that f is equal to g times AX. And we know that if F is computable by full rank ABP, then F is equivalent to IMM. And if you study the Lie algebra of IMM, you sort of understand the Lie algebra of an equivalent polynomial, because the Lie algebra of equivalent polynomials are related. It's GF, if F is equivalent to G, GF is A inverse GG A, where A is the matrix that makes it equivalent. So what we are able to show that if you sort of pick a random matrix in the Lie algebra, then with high probability this has distinct eigenvalues. The Lie algebra of if in this, and then that sort of helps us to compute the so. So you look at the operation of GF on Fn, and you look at the invariant spaces of, so you have an invariant space with respect to a matrix. You can look at invariant space with respect to a vector space of matrices. That's exactly your GF. So you look at the irreducible invariant spaces of with respect to GF, and that sort of that has a very good connection with the layer spaces of F. That sort of if you could compute that, then you can compute the layer spaces as well. And yeah, having this distinct eigenvalues helps us to do that. This is the algorithm. You can compute a basis of the Lie algebra of F, and
from F.
Yeah, from F.
Just by querying it.
Just by querying F, because you can compute this. You can construct black boxes to this. This is very easy. And then you can construct black boxes to this, and then you can construct a basis of that. And then, so you have a basis of the Lie algebra. And since you have a basis of the Lie algebra, then you pick a random matrix from this Lie algebra. And then you can show that this would have distinct eigenvalues, irreducible. The characteristic polynomials has distinct irreducible factors. And that sort of helps us to compute the invariant spaces, reducible invariant. Yeah. So the shifted partial, I just said that this notation is shifted partials. It's
like a tangent.
I don't understand that. Yeah, like is it okay? Yeah. I think I'm done. Yeah.
Okay. Are there questions? Other questions?
Are you simplifying F to IMM? That is what your question is? Yeah, you sort of study IMM, and then that sort of helps you to study F as well. Like F is equivalent to IMM. So it reduces to basically studying this equivalence test. So equivalence test is essentially you are given F and you are given IMM, fixed family of polynomials. You have to just say whether they're equivalent, whether there exists an A such that F is equal to IMM A times X. And this has also been studied in the affine. There's a paper by Neeraj, affine projections paper. And yeah, so I didn't get your question. Are you reducing the problem to G meaning?
Finding a better G for which you can solve it.
No. So this, we are looking at IMM and just studying IMM.
Just that you know the Lie algebra of IMM very well. So
Yes.
you can use that to differentiate.
That's exactly what I was trying to say. Getting the Lie algebra of IMM helps you to sort of claim many things about the Lie algebra of F because of this relation.
Then realize that this full rank ABP.
Yes.
So I think then I could just give up something back to the.
Is it? Because I have, I don't know. Maybe. PIT, yes, we need to do PIT, but not for full rank ABBs. But that is, we have randomization at our hand.
I have a question. So you draw this linear forms at random
Yes,
to ensure that they have full rank.
yes,
So do you need this randomness at some other point in the analysis? Or
yes,
just-
yes, yes.
Okay.
But that is the input distribution. That doesn't come into the algorithm. That is how the input is drawn. But this randomness, we need randomness at many points.
I mean the randomness in the input, so that you draw this from the distribution. So
Yes.
This you need only to ensure this that the ABP has full rank. This is the only point there.
So, are you asking me why is the algorithm randomized only because
no,
of this?
No, I just want to know whether this is really an average case analysis or whether it's just a promise problem where I have to give.
Is
Actually, a problem.
It's a promise problem.
Yes.
So I give you the promise full
Yes.
rank and then you can take the worst case.
Yes, yes, exactly. It's a
If it is not full rank, what happens? The A's become bad.
yeah. If it's not full rank, yeah, this characterization would not
So
hold.
when you start trying to compute that basis, that
Yes.
step will fail.
Which
Usually
The basis of the Lee
Yeah.
algebra, because there you're assuming the next full rank.
yes, yes, yes,
usually that will be just zero. You
zero.
won't get any non.
Okay, you'll get all zeros.
Any more questions? Okay, so then
Yeah. Thank you.